Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thanks. So today what I'm going to talk about is to talk about this is a useful feature in my mind for network control when we want to control Ethernet. So in sort of this morning's talk, there's several people talking about how to use a centralized sort of control plane, come up with the optimal routing strategy, and then you can deposit into the forwarding table of network devices, routers or switches. So for routers, there's no problem. You can just directly deposit them into the routers. But the question is, what do you do with Ethernet switches? If you don't want to change the layer 2 devices. So let's review Ethernet routing as it stands today. Basically, it's based on spanning tree. Even if you have mesh-like physical network, you are going to route your packets on a spanning tree to avoid loops. And then you try to use the source learning to try to populate the forwarding table. And in the case that it doesn't know what to do with the packet, it broadcasts. So the question is that how much control can we exert on the forwarding tables of Ethernet switches? And the answer is a lot. You can actually just use VLAN to control the routing if you want to. And this is really a hack of how you can actually control the forwarding tables of the Ethernet switches. So just an introduction to virtual LAN. The idea of virtual LAN was originally proposed to support multiple IP subnets on a layer 2 network without layer 3 routers. So in the old days, they think that layer 3 routers are slow and expensive, and therefore they say, wouldn't it be nice if we can just have a layer 2 network and support different groups which are on different IP subnets, and yet you don't really need routers to stick it in between. So the idea is VLAN is that it can actually limit the scope of a broadcast packet within the members of that VLAN. So that's basically the idea. And what you do is you actually stick a 4-byte AO2.1Q header between the source MAC address and the standard type and length field of the Ethernet header, where the first 2 bytes is basically indicates the AO2.1Q type. It has this particular number. And then it has the other 2 bytes. 3 bits for priority, and then the other 12 bits for VLAN ID. So in theory, you can have 4,000 VLAN in a single network. So this is an example of typical use. And this is a copy from Cisco. So you can see that there's a Cisco router and so on. So there's actually, in this particular case, you see that there are the single Ethernet network that are connected through these 3 Ethernet switches. They can actually be segregated into 3 virtual LANs. So 1 for engineering, 1 for marketing, and 1 for accounting. And the good thing about this is that they don't have to be physically together. Members of a VLAN group can be sort of spread across geographically, across the enterprise. So that's the idea. And it allows you to actually logically segregate or group the different end hosts into IP subnet. And even though they live on the same layer 2 network, they actually belong to different IP subnets. So in practice, what you do is that you can actually insert this AO2.1Q tag either at the hosts or at the edge switches, depending on whether your end host is supported or how you configure it. And packets exchange between 2 VLAN have to go through a router, because remember, typically a VLAN corresponds to an IP subnet. So when you want to exchange packets between 2 VLAN, you have to go through router. Conceptually, this is actually a very important point. Conceptually, you can think of a VLAN just like a physical LAN that you have today, except that it has its own spanning tree and it has its own layer 2 routing table or forwarding table. So when a packet with a particular VLAN ID comes in, you can think of it that way, that the switch would actually look at the VLAN ID and look up the corresponding forwarding table and forward it. All right. So eventually, the switches that support VLAN eventually already give you multiple forwarding table, 1 for each VLAN, right? Conceptually, that's what you can think of. And moreover, there's this new standard called AO2.1X, allows a so-called per VLAN spanning tree. It used to be the case, like somewhat lower end Ethernet switches actually use just 1 spanning tree for all the VLANs on a single layer 2 network. Now you can actually allow each VLAN to actually has its own spanning tree, and that's kind of important for fault tolerance reason. Like if one particular VLAN, the spanning tree associated with the one particular VLAN dies, you can switch to another VLAN because it already has its spanning tree built up. You don't have to go through the complicated AO2.1D distributed spanning tree reconstruction algorithm. Unfortunately, in commercial switches, the number of VLAN supported is very small, like probably up to hundreds. Lower end one probably give you 64. That's pretty much it. So the higher end one can give you hundreds, but never thousands, okay? Even though, as I said, that the total number of VLAN could have been 4,000 because you have 12-bit VLAN ID. And when you specify a VLAN, you can use a port-based or host-based. Like typically people who don't know better, they just use host-based. They just say, I want this machine to belong to one VLAN. All right, there's nothing wrong with that. You can specify it that way, and the switches would actually configure it and then find the spanning tree for that particular set of hosts that form a VLAN group. Or you can do port-based. This is something that allows you to have strict control. You can actually say that I have 3 switches, and I want port 1 of switch 1, port 10 of switch 2, port 29 of switch 3 to form a VLAN. So you can say something like that, and then it will form a VLAN group just like that, as what you specify. Now imagine if you have something like this. You have a port-based mechanism to specify a VLAN's membership. Then what you can do is you can actually construct arbitrary topology for that VLAN, right? And then you can actually form a path if you want. If you can actually have a path for a linear topology for a VLAN, a linear chain of switches, for example, for a particular VLAN. So essentially VLAN gives you a mechanism very similar to ATM. Let's say you want to force a particular route through a series of switches. All you have to do is just to specify the proper ports of the constituent switches, and then you can form a path. So it allows you this mechanism to force a particular path through a particular network if you want. So we use this mechanism to do something similar to 4D project is trying to do. This particular project is called Viking. It's basically a network resource management system specifically for campus-wide layer 2 network or for Metro Ethernet. So what we are given is just a layer 2 network. It's a very large layer 2 network. And what we want to do is to do all these goodies, load balancing, routing, fast failure recovery, and so on. So the major problem is I say that the existing Ethernet is that it is inefficient because it has a single spanning tree. So everything has to be routed through this single spanning tree. So it's not particularly efficient in terms of resource utilization. And it's inflexible routing. You have to follow the spanning tree, so you cannot always use a shortest path routing. And it's longer failure recovery because of a single spanning tree. When that particular spanning tree dies, you have to spend up to 30 seconds to reconstruct another spanning tree just to make it. And of course, there are newer standards that try to reconstruct the spanning tree faster, but still it takes on the order of seconds. So what we want to do is to say that given a layer 2 network, how can we do traffic engineering using VLAN as a control mechanism? So basically what we do is very simple. Constantly measure the traffic load matrix. You know for a given pair of nodes how much traffic is going on. Now you are going to compute an active and backup path for each node pair. So that's the standard graph algorithm. You can compute something like that in order to balance the loads among the links. And if whenever possible you want to use the shortest path. And then you are going to force for a particular pair of nodes a path using this VLAN mechanism. So it allows you, gives you this capability of ATM-like behavior on top of Ethernet. And eventually, because we only have a finite number of VLAN we can work with, so we have to sort of combine this logical VLAN, one for each node pair, into one physical VLAN, because we only have a finite number of them. And that's the idea. So in the big picture, what we have is that each host in a single IP subnet will participate in actually multiple VLAN. So in order to get to as a particular host, in order to get to node 1, I probably use VLAN 1. In order to get to node 2, I probably use VLAN 12, and so on. So, and which one I'm going to use depends on that routing table that I built up at the end hosts. And for fast failure recovery, since I have 2 VLANs to get to a particular destination, one for primary, one for backup. So if one of the current VLAN dies, I can switch to another VLAN. So we can also use this mechanism to support some sort of QoS if we want. Like, you want to force a particular group of nodes to use a certain amount of resource. You can do it. You embed that decision into the routing computation algorithm. So this just give you a sort of a taste of what this thing can do. This is basically a simulation result. We have a prototype has 10 nodes, but we cannot grow this to 64. I think this is an 8x8 grid. So this shows that. So what it basically shows is that you give a pairwise, equal distribution of load, all right? And then the x-axis shows the number of switches in the network, and y shows the total throughput you can, sustain. So as the number of switches grows, the amount of load also increases, all right? So they will be increasingly have some kind of congestion, and as a result, the traffic actually the total throughput will actually decrease. So the lower line corresponds to the standard design, single spanning tree. And the second line, the red line, corresponds to multiple spanning tree with backup. Right? We have to reserve some resource for backup. And the third line corresponds to multiple spanning tree without backup. Okay, so I'm going to skip this. And then we also use these same ideas of VLAN to try to use Ethernet switches as a building block for storage area network. In storage area network, the very important primitive is multicast. Let's say you have an NFS server or database server. They want to talk to storage server, iSCSI storage server. And usually you want to do some kind of replication, primary storage server, local mirroring, or remote replication. So you want to do this kind of multicasting. But in a layer 2 network, when you do multicasting, you basically use broadcast. You do broadcast and do endpoint filtering. That's what happens. And VLAN actually can give you can actually structure a multicast distribution tree for you using VLAN. Because again, you can carefully construct the VLAN by, designing a tree-like topology for a VLAN and use that as a distribution tree from something like an NFS server to all the storage server. And as a result, you can do something like this. So, for example, in this case, the left-hand side is a storage client, and you have two storage servers. So what you are going to do is that when you have 3 iSCSI requests you need to send, you can actually merge them and send them into a single multicast request, the payload part, when you want to write. And you can actually send to all the other 2 storage servers in a single request. But in order to get reliability, at the higher level, you still think there are 3 TCP connections going on. So the reliability is taken care of this unicast, ACK, and retransmission. But the forward path is taken care of through this unique multicast common data for the write requests. So by doing something, we can transparently merge the common payload of 3 write requests into a single layer 2 multicast packet. And in case some of the packet did not get to one of the storage server, you will send the ACK or through some kind of retransmission through the unicast connection going through this layer 2 network. So that's the idea of this Cassini project. So my main message is that there are many interesting and innovative features in commodity Ethernet switches. So as I say, VLAN is just one of them. There's such a thing called IGMP snooping, and there's such a thing that it allows you to do some kind of priority. So you can actually use it to do some kind of quality of service guarantee. But they are largely unexplored. People tend to think of them as something that you can do statically. They don't think of it as a dynamic reconfiguration primitives, when in fact they can be used that way. So because a lot of these primitives, like command line interface or SNMP or HTTP, you can actually use this control primitive to control how these Ethernet switches should be configured to do the kind of thing that you want. So you can do this according to the traffic workload or even hardware health status and so on. So today I only talk about sort of very simple examples of application, like you can use this control mechanism to control or to maximize the resource utilization of large-scale layer 2 network or for storage area network. You can also think about how to use this for compute cluster interconnect, like you can configure a network topology according to program communication statistics and so on. So I think that's it. Questions?
So what kind of frequency can you sort of do this kind of reconfiguration?
The configuration time is on the order of 2 to 5 seconds.
Okay.
Yes.
And how do you communicate to the switch?
Through SNMP.
Right, but then through the IP connectivity to...
That's right. That's right. So if we don't have a separate control plane.
Connectivity to the switch is separate. Another VLAN, how does it work?
So for now, it's a separate VLAN, yes. So there's a single control VLAN that spans everybody.
What if that VLAN fails?
The VLAN fails, then we don't have anything. That's right. So this is something that you have to live with the commodity switch. This is because we don't want to have a separate control network for control. So we can only leverage whatever is existing there.
That control sort of channel, sort of we call it dissemination, sort of in the 4D. Is that possible to use multiple VLANs?
Sure.
And use the same technique
Sure. Of course. Sure.
Okay.
That particular control network, you can have redundancy into it, just like a normal source and destination pair.
Okay.
Yes.
Okay.
Yes.
Is there a limit on the size of a network that you can calculate given the restrictions? You said 4,000 being the upper bound of number of VLANs.
Probably that's the limitation, the total number of VLANs. But as I say, we have to aggregate. So in order to scale up, the only thing we can do is we have to aggregate multiple logical VLAN into a single physical VLAN. They have to share the same physical VLAN. And the price you pay is that whenever you do broadcast, you will reach everybody. All the logical VLAN in that physical VLAN. But no, so the point is that the idea of having multiple VLANs on a single layer 2 network is well known. Today they only use it for segregation, right? Different departments have their own VLAN. What we are saying here is that you could have just used it as a control primitive. For a single VLAN, you could have just used it to do what you want to do. Things like load balancing, fast recovery, and so on. Right? And I see that there are actually people who are trying to move this idea into the standard. That, you know, multiple spanning tree, for example, it's not very clear whether hardware vendors would actually implement them. But one can show that you can already do this with the software. Yes?
Multiple spanning trees was patented by Phil Karn in 1984.
Mm-hmm.
We've had multiple spanning trees for a long time.
Yes.
Multiple spanning trees was patented by Phil Karn in 1984.
Yes. So there are actually some interesting twists to this multiple spanning tree idea because, you know, just because you say you want multiple spanning tree, you also can ask the question, what kind of multiple spanning tree? You have a spanning tree like this, you want to have a notion of complementary spanning tree so that you can use up as much resource as you want, right? So it's, you know, it's multiple spanning tree is sort of pretty obvious, but, you know, how do you do it right? It's not very simple. Yes?
Did you look at radio Perlman's successor to spanning tree?
So there are various like AO2.1W and various kind of algorithms that try to solve this problem of how to do low latency failure recovery. Right? I guess that's along the line that you are suggesting.
Well, in particular, I think she has some reason for it that talks about multiple active links.
Yes. Yes. So I'm not really aware of that particular work, but I'm aware of like in a standardized community, they try to solve this problem, fast failover problem, and they seem to be already sort of draft and even sort of pretty close to standardization stage to actually solve that particular problem. But this particular approach try to solve both load balancing, you know, and latency and failure recovery by saying that whether we can use a commodity switch as a control and the VLAN mechanism on commodity switch as a control mechanism. So that's the sort of distinction between, you know, what people are doing and what we are doing. Yes.
So, you know, there's the world of layer 3 routing and IP configuration, the world of Ethernet, and it seems like they're rapidly growing together. I mean, the IP people are trying to make it as plug and play as possible, which is always the advantage of Ethernet. Ethernet is trying to add all these advanced functionalities like
yes.
engineering and whatnot.
That's right.
So, will there be convergence? Is there a happy medium? Is one better than the other for certain?
I'm probably not in a position to say something like this. So from my point of view, I'm just trying to advocate that, you know, it seems that people tend to sort of ignore even the kind of feature I'm talking about, even are existing in D-Link switches, right? We are not talking about Cisco. D-Link. So that's probably like a, you know, a factor of whatever difference in terms of price. But for those low-end switches, it actually have a lot of features that could have been exploited. And, you know, the question is that how do you do it and whether it's feasible with that kind of time frame, like 1 to 5 seconds, you can actually reconfigure and so on. Of course, there are always reliability problems. Like you use the switch say it's already reconfigured and, you know, you don't trust it because, you know, the software there is buggy and so on. It's possible. That's definitely possible. But, you know,